So the next one is 10. So here a and b are integers not divisible by the prime p. We then have to establish this following congruences. If the pth powers of a and b are congruent to each other modulo p, then a and b are also congruent to each other modulo p. And if that same congruence is true, then the pth powers are also congruent to each other modulo p square. Okay. So let's see the solution. Part A is actually quite easy. It follows almost directly means immediately from Fermat's theorem. So Fermat's theorem gives us these congruences. And b to the power p is congruent to b modulo p. So if the pth powers are congruent to each other, then obviously the original numbers will be congruent to each other using these three congruences and the fact that congruence modulo p is transitive, is a transitive relation. We have this. Okay. Now next part B. Alright, so in part B, we are again given this congruence, but now we have to prove that a similar congruence is true where the modulus is p square. Now from part A, what do we see? That A is congruent to B mod P. I mean, you have this condition here, that same condition is also there in part A. That means we can now use this fact. So, from part A, we have A congruent to B mod P. So, A will be of this form, B plus Kp for some integer k. Alright. Now let's consider the difference of these two pth powers, a to the power p minus b to the power p. So we are going to substitute this expression for A, that is B plus Kp whole to the power P minus B to the power P. Let's now expand this using our familiar binomial theorem. So that will give us this. I mean, if I simply just write the sum, let me first write the sum itself, and let me just write it and then I will say something. where I varies from 0 to p. So what I wanted to say about this expansion is that you may think that I should put p to the power I and kp to the power p minus I. Yes, I can, but I can also write the expansion like this. It does not matter, we get the same thing because b plus kp is equal to kp plus b. And if you expand this sum means if you write it fully without using the summation notation, whether you consider this or you consider this other sum, other sum means the appearance is different. You will see that when they are written as sums, they are the same thing. So it does not matter whether I write this one or this one. However, this one is going to be useful to us. Minus b to the power p. Now we are going to separately write that term of this sum which corresponds to I equal to 0. That means p choose 0. So if I is equal to 0, this term will not be there. Will not be there means it will be 1 and we will get this. So now I starts from 1. I times b to the power p minus I minus b to the power p. Because p choose 0 is 1, so this b to the power p and minus b to the power p cancel out. And we have, I should have written plus. We have this. Now from this sum also again we are going to separately write the first term. There is a reason. So if I now write the term corresponding to I equal to 1 separately, I get p choose 1 times kp times b to the power p minus 1. And now I starts from 2. Alright. Now note one thing that p choose 1 is p, we already know that. In the alternative notation, it's written as pc1, which is p. So we are getting 1p from here and already we have a p here. So we get kp square times b to the power p minus 1 plus. So this term is divisible by p square. What about the terms in this sum? They are also, each one of them is divisible by p square. Why? Because you can see that p to the power I is appearing. Alright. And I starts from 2. So each term has at least p square. It can have a higher power of p, but at least p square is there. That means everything here is divisible by p square. So this is an integer divisible by p square, and that is why this is congruent to 0 modulo p square. So going back to where we started, a to the power p minus b to the power p is congruent to 0 modulo p square, and that's why we have our required congruence now. Okay, so that's how we have this. Next, number 11. Imply Fermat's theorem to prove that if P is an odd prime, that means P is not 2 but P is prime, then here also there are two parts plus so on p minus 1 to the power p minus 1 is congruent to minus 1 here modulo p. So this is one congruence, and in part B we have this 2 to the power p plus 3 to the power p, p minus 1 to the power p. This is congruent to 0. Yes. All right. So solution. Part A. For any integer I in this range I is relatively prime to p, because p is a prime and p does not divide. Actually this has nothing to do with p being a prime. P is a positive integer and p will not divide any positive integer I which is less than itself. So by Fermat's theorem, what can we say? I to the power p minus 1 is congruent to 1 modulo p. And now we can use this congruence or these congruences because I can vary here. Hence, this sum is congruent to 1 plus 1. So we are using these congruences to these terms. You to understand how many ones we have here, p minus 1 number of ones. So that is congruent to p minus 1, which itself is congruent to minus 1 modulo p. So we have our first congruence. Then the second one, Note that so far we did not have to use the fact that P is an odd prime, but now in part B we will need that information. In part B, we do not have P minus 1th power, but rather Pth powers. And here it's more direct by Fermat's theorem. So this pth power is congruent to the base. A to the power p is congruent to a modulo p. And this congruence, which is a consequence of Fermat's theorem, actually it's not the Fermat's theorem itself, but it's a corollary to that, is independent of the fact that whether p divides a or does not divide a, it works in both the cases. So just like that, this pth power is congruent to 2. This one is congruent to 3. This one is congruent to p minus 1. Now you use your familiar sum of the first in natural numbers formula. So by that formula you have p minus 1 times p minus 1 plus 1 divided by 2. So that means you are now having p minus 1 divided by 2 times p. Note carefully that since p is an odd prime, so p minus 1 is an even integer, and that's why p minus 1 divided by 2 is an integer, and that is why this is an integer multiple of p, and that is why it's divisible by p. Otherwise we don't really know. So that is why this is congruent to 0 mod p. In fact, you can write a small line here. Note that since p is odd, p minus 1 divided by 2 is an integer. Okay, so that's the solution. Let's see another one. Number 12. Prove that if p is an odd prime and k is an integer satisfying these inequalities, p minus 1. So k is a positive integer less than p. Then the binomial coefficient p minus 1 cubes k is congruent to the kth power of minus 1 modulo p. We already know from combinatorics that these are integers, and in fact positive integers. So it makes sense to at least consider it as a part of a congruence. Alright, so how can we establish this one? Note that Let's start by considering this binomial coefficient multiplied by k factorial and see what we get. K factorial times this. So if I, instead of straight away using congruence, let me first write equality itself. So if I use the definition of this, what do I get? P minus 1 factorial divided by P minus 1 minus k factorial times k factorial. That means we are getting this. Now if I start expanding the numerator, it will go like this: p minus 1, p minus 2 and so on. Eventually at some stage we will get to this. But what is the term before that? To get the term before that, you just have to add 1, because these are decreasing by 1 each time, right? So adding 1 to this, you get p minus k. Okay, so that means after cancellation you have this. And now congruence comes. Because p is congruent to 0 modulo p, so this is congruent to minus 1 times minus 2 and so on minus k modulo p. I will write mod p afterwards. There is still something else to write here. So now if I collect all the minuses together, how many factors do I have? 1, 2, 3 k factors. So this is congruent to minus 1 to the power k times 1 times 2 times 3 and so on up to k. That means k factorial, and now I write mod p. Now you look at the first and last things. We have k factorial times this on one side, and on the other side we have k factorial times this. Since k satisfies these inequalities and p is a prime, so this is equal to 1. Why though? If not, let me just break the solution, and in the middle itself, let's try to understand why this is so. Say this is not 1. What does that mean? That this GCD is greater than 1. Now GCD by definition is a divisor of both k factorial and p, and also GCD is positive by definition. However, p has only 2 positive divisors. Being a prime, the positive divisors are 1 and p. And we are saying that, say this is not 1, that means it has to be p. But then the GCD is p, which means that p has to divide k factorial. But what does that mean? If I write k factorial as a product, I get this. Now recall one of the properties of a prime. When a prime divides a product of some integers, then it has to divide at least one integer. So p has to divide I for some I here. in this range. But is that possible? I is a positive integer and I is at most k. K itself is less than p. So no, p cannot divide I. Because of this reason, this has to be 1. The other possibility that it is p is not a possibility at all. But now you recall from the theory of congruences that when you have the same integer on both sides of a congruence, you can cancel it from both sides. Just like you can cancel the same thing from both sides of an equation, ordinary equation. But there also there is a condition that the thing you are cancelling should be non-zero. The version of that condition that we have for congruences is that it has to be relatively prime to the modulus. We have that now. So hence, we can cancel it, and cancelling k factorial from both sides, we get our congruence. That's it. So let's just end the video here itself. Tomorrow means Tuesday, and I think if I am remembering correctly, last Tuesday we did topology. In fact, we solved exercises, I think. So tomorrow we have to go back to differential equations. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.